Welcome to Simple SIMO. I was asked to do kind of a condensed version of simultaneous observation and try and make it a lot shorter. So this is about a 10-minute version. Basically, simultaneous observation made simple. I hope everybody's doing okay in the world based on what's going on with the current situation. Simple SIMO, again, we're talking about two models, globe model and the flat Earth model. When we do observations to the sun, measuring sun angle to the sun, the globe model has only 45 degrees surface angle to work with because they've used up 45 in the curve, and this is at a distance of 3,000 miles. And the flat Earth model has all 90 degrees to work with, so flat Earth model has an advantage there. So basically, to break it down very simply, when we talk about one of the big objectives, or the main objective of this whole operation, and that is taking, I coin it, taking the Black Queen, or removing the heliocentric globe model long distance game piece off the board, or the Black Queen. And basically what we want to do is we want to show that not only is the surface of the Earth flat based on angle to the sun, measured angle to the sun from the Earth's surface, but also we can prove through triangulation that the distance of the sun is only 3,000 miles. So we want to bring that sun back in from 93 million miles, or the heliocentric science says it is, to its rightful place of 3,000 miles. And we want to take that long distance game away. Just kind of an update, Operation Resolute Time, and that's the ongoing operation measuring sun angle and getting sun timing down. It's going. We're showing really good findings, significant findings actually. As a result, we've been measuring angles to the sun of over 50 degrees at 6,000 feet. This gives pretty credible evidence to support the existence of a firmament. In other words, when we talk about that, we talk about the sun. We're measuring azimuth as well. The azimuth is staying the same, but the elevation, it's increasing in elevation. So the sun, or its projection, is climbing along an arch as it moves through our sky. This also gives more direct evidence against the heliocentric model that the sun is moving in a linear projection only as it moves through the universe. So a real big finding right there. I've had to develop what's called a Marks device. It's a sun positioning device, and it's pretty handy. And basically what it is it's a 6 by 18 inch piece of wood with a center hole cut in it, and then a line strung across it about 4 inches, and gives a when the sun reflects on it, gives a shadow of the perfectly 90 degrees sun line for sun position. And this can be shifted. Initially, when we set up our position, it was west a little bit early, too far west, so we had to move it and develop the Marks device, and that kind of really helps us get sun timing as well as sun position down. It's really a great tool. And again, this is oriented north as well, so we orient it in with a compass. This is actually what it looks like, the Marks device. As it says, just a simple piece of plywood, 6 by 18 inches, center hole cut in at about an inch. It's fit a bottle cap through it, and that's what we're using to mark our survey point. And you want to set that right over the survey point, and then you have the suspension string, 2 nails, center line, and then when that sun moves right over the top of it, it gives a perfectly 90-degree grid line. And again, this is oriented north. It's oriented, put in with a compass. Again, simultaneous observation. We look at again, we're measuring sun angle, and again, when we look at that, we have to, for the globe model especially, we have to, the total composite angle cannot exceed 90 degrees. So when we measure that surface angle to the sun, and again, the sun is the EOL, or the end of the orienting line, so you can only go up 90 degrees from the Earth's surface on SIMO. So the globe model has only 45 degrees to work with. It can't exceed it. Otherwise, it's out of tolerance. Okay. Again, we're using 2 observers, same elevation, 3,000 miles apart. Okay, and if we have readings that exceed 45 degrees, that means there's no curve present. If we have in this example, if we have a reading here, we have two observers, and they get a reading of 55 degrees. This is the problem that we have, and when we apply this with the globe model, we then exceed the 90-degree tolerance. We're then over by 10 degrees, and when we look at distance, you're now off sun target by 16 million miles, over 16 million miles. So that's the problem. And again, this is almost like U.S. military uses a weapons bore sighting. You now have two 90-degree angles going in an object that's 3,000 miles apart, and we can tell how far off sun target you are just by the angle. Then, very basic, very simple. Again, as I said, this is an example of what I was talking about, similar weapons bore sighting. Now we have lines in parallel, two observers at 90 degrees. Remember, this is a measured 90-degree angle going right into the sun. And because we got a reading of 55 degrees, we're now off sun target. We're actually over the sun by 10 degrees, which is 16.5 million miles. We're only using sun half width, which is about 480,000 miles at 93 million miles. And again, this measurement comes from the flank, or the second observer. So that's a huge problem for the heliocentric model, or the globe model. And right now we're exceeding 50-degree measurements at 6,000 feet. So that's a big problem. And how do we get this data? How do we get that angle? Basically, a right triangle data calculator. We just input our given data, 93 million miles and some change, and then a 10-degree angle, and that gives us our result just over 16.5 million miles. Again, take away the sun half width, and you're still just over 16 million miles off target if you have readings over 50 degrees. So that's quite a problem. I was asked to explain SIMO correction factor, and again I'll cover that again just real quick. Again, we have both of our observers sighting in on the sun. This is a timed observation event, so the sun has to travel between observers at 3-hour mark. So when the you start time when the sun is 90 degrees to the first observer, and then the second observer sights in on it, gets their angle, and then as this example, they measured an angle of 50 degrees to the sun. Now, as the sun travels, the 3-hour mark is reached here. That second observer from 90 degrees comes to that 3-hour mark and measures. Now they come up with a measurement of 85 degrees. That gives us a correction factor of 5 degrees. That means that this distance between the two observers, okay, is a positive correction factor. That means the sector is too long. So we have to add that. We would add that to our 50-degree reading. That would give us 55 degrees. And again, this is a factor that I built in based on distance and sun timing. That's why it's so critical. You may get a shallow or a high angle in the initial reading, but you're going to pay or you're going to own up on the backside where the other observer is. And again, this is kind of a check factor built into this this test box, what I call the test box. In the other example, we're going to give a negative factor, and that is the sun starts here, moves, but it passes the second observer, and it's not 3 hours yet, but it reaches the 3-hour mark here. So the second observer is going to go from 90 and measure the sun. He gets a measurement of 85 degrees. That gives us a negative correction factor of 5 degrees. So now we take that, subtract it from our initial 50, and we get a 45. Now that would bring the globe into tolerance. That meant that this sector was short. The distance was short. Okay, so that's basically how the correction factor works. And again, with time distance sector validation test. It's very critical and very important. And then finally, when we look at what does this all mean when we get these surface measurements, and we can break it down real simple. We're doing measurements at half meter and 1 meter. So in this example, if I have a half meter measurement of 54 degrees and a 1 meter measurement of 53 degrees, which you're going to get, we've been finding that you get a 1 degree difference. We would then take that half meter, because we want we would take that half meter 54 degrees, and we would add the one degree to it, and it would give us a true surface angle from the very surface of the Earth to the sun at 55 degrees. Our result would be the Earth's surface is flat. That would be our result. Again, anything over 45 degrees knocks the globe model out. So it's very important. Again, this has been simultaneous observation, SIMO, simple SIMO, and I hope I've kind of cleared up some things on it. If not, you can ask questions and reach me at coryifish@gmail.com. Stay safe out there, and thanks for watching.